This tape looks at the facts and figures involved in the serial transmission of digital video and audio signals down a single coaxial cable. We will show that the system accommodates both component and composite signals. Here is an example of a typical path for a component signal through a serial digital interface, SDI for short. This will help locate each process as we explain them in more detail. We have started with analog RGB, which is coded into component Y, R-Y, and B-Y, and the color difference signals attenuated to CR and CB. The signals are low-pass filtered. The Y signal to 5.75 MHz and CRCB to 2.75. They are now ready for the analog to digital conversion. Y is sampled at 13.5 MHz and the color difference signals at 6.75. This is called a 4:2:2 component signal, with the numbers referring to the ratio of the sampling frequencies. Historically, unity was defined as 3.375 MHz, or 216 FH, meaning 216 samples per total line. Therefore 13.5 MHz equates to 4, or 864 times FH. These sampling structures conform to CCIR 601. We now have 3 10-bit digital channels ready for the next stage of processing. The data is multiplexed into one 10-bit channel, and digital syncs are added. Ancillary data, such as audio, can also be multiplexed into this stream. It is at this point that data can be transferred between equipment, using a 25-pin D-type connector, the layout conforming to the CCIR 656 standard. Using a single coaxial transmission system gives us many advantages over that of a multi-conductor one. Longer distances can be achieved, routers are smaller and simpler, and they can use existing cable, making the system extremely cost-effective. The multiplex data is serialized into a single bit stream and finally input to a line driver. It is now capable of traveling typically 200 meters on good quality coax cable, as found in most TV studios. It enters a receiver which consists of an automatic equalizing amplifier, a clock recovery circuit, and deserialization back to a 10-bit parallel multiplex signal. The 25-pin D would also be at this point. The signal is now demultiplexed to 3 10-bit YCRCB channels, and the audio extracted. The video may now be D to A converted and decoded back to RGB. We will now look at the individual processes in more detail, starting with the sampling process at the A to D converter. The samples are coherent and form part of an orthogonal sampling structure, which means that corresponding samples on adjacent scanning lines are aligned vertically, so the positions of corresponding samples on all lines are the same. This lends itself to better data manipulation, especially where interpolation is required. At the output of the A to D converter, YCRCB samples are aligned like this. We'll be returning to this structure later. The number of samples per active line is the same for both 525 and 625 systems. 720 for luminance and 360 for each of the color difference signals. The total line lengths for both standards are different. 525 having 138 in the horizontal blanking period, and 625 having 144. The luminant sync edge timings occur after 16 samples for 525 and 12 for 625. These waveforms show the quantizing levels using 8-bit notation, and it should be noted that 00 and FF are forbidden levels, as they are reserved for sync information. Because we have only digitized active video, horizontal and vertical syncs are not present in our digital signal and must be reintroduced in the form of timing reference signals, TRS for short. They are called SAV and EAV, start of active video and end of active video. This waveform shows the timing of the samples. And here is the full structure of these signals. Each consists of 4 words. The first 3 are a sequence of reserved hexadecimal numbers, FF0000, used to easily identify SAV and EAV. The 4th word starts with a 1, followed by 3 flags FVH, some protection bits, and 2 trailing zeros. F indicates the field, 0 for the first and a 1 for the second. V is a 1 during the field blanking interval. H is a 0 for SAV and a 1 for EAV. The protection bits are similar to the Hamming codes which are used in teletext. You may have noticed that all these numbers are in 8-bit notation, which we used for simplicity. 8 bits are becoming history, as most systems are now geared to 10 bits. When upgrading a system from 8 to 10 bits, it has to be decided how to denote the change. Do we add 2 preceding zeros or 2 trailing zeros? Both are correct, but the end user must know which form is in use. Adding the 2 extra bits gives us 4 times the resolution. For every original step, we now have 4. Let's look at these signals in both 8 and 10-bit notation, as seen on this analyzer. Returning to our signal and looking at the data space available in the horizontal blanking period, we can see that there is space for ancillary data. This is called HANC for short. This can be used for audio channels and at present uses 4 or 8 AES EBU coded signals with data space left for future use. There is also ancillary data in the vertical interval called VHANC. Lines 20, 21 and 22, 333, 334 and 335 are reserved for this purpose. It is possible that vertical interval timecode may conflict with this reserved data if current practice of using lines 19 and 21 continues. At the present time, the timecode is digitized as part of the video signal. This is the multiplexing circuit, showing the combination of TRS and ancillary signals with the multiplex data. First, the YCRCB is multiplexed into a repeating sequence of 4 words. The first 3 are co-cited and are transmitted CBYCR. The 4th being the next Y, which is on its own, but of course still part of the overall orthogonal pattern. The next stage allows for rounding if activated. Limiting is also required, so that any zeros are incremented to 1, and any FFs decremented to FE. The data, now free of zeros and FFs, is multiplexed sequentially into a single 10-bit parallel channel, which includes the ancillary data and TRS signals. The clock frequency is now higher at 27 MHz and is made up of 13.5 plus 6.75 twice. Clock information is transmitted separately. As we have said, this can appear on a D-type connector and conforms to CCIR 656. At this point the signal is balanced with a peak-to-peak level between 800 mV and 2 volts peak-to-peak. This is across a 110 ohm resistor at the output terminals, but without a transmission line connected. Here are the pin allocations of the connector. It is interesting that this connector and layout are also used for composite signals. The same interconnecting cable can be used by both systems. The differences being the clock frequency and the data format. It must be stressed at this point that the signals are not compatible, but use a common path for transmission. Our component signal, now in 10-bit parallel form, is put into a 10-bit by 3-word shift register to be serialized. However, up to this point, the channel coding method used is NRZ, non-return to zero, a code represented by voltage levels, and, as we can see, not polarity independent. The system as it stands is suitable within a closed digital environment, using a separate clock signal to synchronize the data. Long strings of ones or zeros, not affecting the fundamental clock timing. However, a single wire system needs to have the clock information embedded in the data stream in a way that can be easily detected and regenerated at the far end, even if the signal has undergone polarity change. This is called a self-clocking system and normally needs transitions to be detected, not levels. It should have minimal LF content with the avoidance of long runs of ones or zeros. To achieve this, two processes are applied to the basic NRZ signal. They are scrambling and inversion. Let's look at these processes in more detail. The circuit looks like this. The signal is scrambled and then inverted. The algorithm for the scrambling is x to the 9th plus x to the 4th plus 1, and we can see it is implemented here with the shift registers, with added feedback. Although scrambled, the signal is still NRZ in form. Inversion to NRZ-I form turns logic 1s into transitions, leaving the logic 0s unchanged. Theoretically, there will be some occasional long runs of 1s and 0s, and they will be discussed further in the tape on testing SDI. So if we look at our main block, we can see that our signal in serial form is now fed to a line driver which feeds into 75 ohms at a data rate of 270 megabits per second and can travel typically 200 meters or more on suitable cable. So the first job of serial decoding is to equalize the cable losses. This has to be done to aid the recovery of both clock and data signals. It uses two stages with variable gain amplifiers applying HF boost, controlled by a peak detector. The LF is corrected by the next part of the circuit. The signal is applied to an 8 MHz high-pass filter, buffered and then sliced. The feedback through the low-pass filter ensures the DC is always slicing through the middle of the signal, shown here. Note that the circuit does respond to peaks, so it is vital that send levels are precisely aligned. The circuit for clock recovery is shown here. The serial data is used to generate edge pulses, which are then compared to the phase of the VCO. which, because it is now phase-locked to the incoming signal, will regenerate the 270 MHz clock pulses. The delay is necessary to allow time for edge processing and ensure correct timing of the reclocked data. Now that we have regenerated a reliable clock signal, we can accurately clock the incoming data into the decoder for descrambling and inversion back to NRZ. It first goes into a 30-bit shift register, then a 10-bit latch, forming once again a 10-bit parallel multiplex data stream, ready to be demultiplexed. The TRS is identified and used to time the 10-bit data latch. The demultiplexing is done by the parallel interface decoder. The data is first detected and split into Y and C, both at the 13.5 MHz clock rate. A 2-bit ANC signal and ancillary data are extracted before the signals are decoded into Y, CR and CB. Sony has produced a chipset which incorporates all the features we have mentioned. The multiplexing and addition of ancillary data and TRS signals is called a coprocessor, and the next stage a serial encoder. The third is a line driver. On the receiving side there is a serial decoder and finally a receiver coprocessor. It is only the coprocessors which are different for composite transmission. So at the heart of the system there are 3 common chips. Having shown the component processing, we will look at the differences when a composite signal is applied to the system. We will start by looking at the way the signal is digitized. One fundamental difference between this and component is that the sinks and burst are digitized as part of the signal. This reduces the effective quantized resolution, so a 10-bit system is preferable. The horizontal blanking period has less space for inserting ancillary data, and this does restrict a composite system to effectively 4 channels of sound. The clocking rate for composite is 4 times subcarrier, 17.7 MHz, giving 1135 samples per total digital line, 0 to 1134, except lines 313 and 625, which have 2 extra samples, making a total of 0 to 1136. These extra samples realign the sampling pulses which have been displaced by the 25 Hz offset, the number of samples per active line being 948, 0 to 947. The sampling axes are 135 and 225 degrees, and the sampling is either 8 or 10 bits of uniformly quantized PCM. In 10-bit notation, white level is D3.0 hex, blanking 40.0 and sync tip 01.0. The following are forbidden levels, as they are used for the TRS signal: 00.0 to 00.3 and FF.0 to FF.3. The blanking conforms to a digital representation of both the horizontal and vertical analog blanking periods. The 10-bit data is applied to the coprocessor, and TRS, ID and ANC signals added. This concludes this tape, and here is one last look at the overall SDI signal chain.